So here we have the gas chromatograph and mass spectrometer, also known as GCMS. Here we're using a similar methodology seen in the GC-FID, where we use the same cell permeation cell setup to detect chemicals moving through a barrier. Here we have two sides to our cell, the challenge side and collection side. The chemical that is permeated is then carried by a nitrogen flow to our GCMS. The main difference here is, instead of using an FID detector, flame ionization, where it will burn up the sample, we're using a mass spectrometer. This not only allows us to detect how much of a chemical is permeated, but also allows us to capture key information about that chemical, such as fragmentation patterns, just to let us know exactly what has permeated. So here we have the gas chromatograph and mass spectrometer, also known as GCMS. This setup is very similar to our GC-FID setup, where we have the same permeation system in cells and nitrogen flow taking the permeated chemical to the GCMS. The main difference here is, instead of using a flame ionization detector, which burns up the chemical to be detected, we're using a mass spectrometer. This not only gives us how much of a chemical is permeated, but also tells us key information about what that chemical is. This is especially important for mixtures. There are multiple ways a mixture could be tested, however some of these give meaningless results. As these aren't covered in the standards, it is completely possible to receive an accredited report that contains meaningless results. Let's look at why some of these may be meaningless. Let's take a mixture of two chemicals. Let's say methanol and toluene, shown here by squares and circles. One common technique of trying to measure chemical permeation is by assuming the ratio that's going in is the same as the ratio going out. Based off this assumption, we're treating this like it's actually a single chemical. We don't know exactly what the ratio is coming out, but we're assuming it's the same. From this testing, the graph looks like the red line here. This is in the case of methanol and toluene. This shows us that something is permeated and gives us some indication of the rate, but it doesn't tell us truly what has permeated. What we strive for is technique 2. Here, the same mixture is poured into the cell, but once it's permeated, the components are separated out and detected individually. This not only gives us how much of a chemical is permeated, but also tells us what has permeated. So for our example of methanol and toluene, this leads to two lines on the graph, one for each component. So why is this important? If you look at our example of methanol and toluene, you look at a point where there's 100% methanol and 0% toluene in the system. At this point, there is no detected permeation whatsoever. However, if we come down to a point where there's 20% methanol and 80% toluene, what we see is methanol permeating at a rate of 140 micrograms per centimeter squared per minute. That's 140 times the BT 1.0 limit. So that means, when pure, methanol doesn't permeate. When in a mixture with 80% toluene, it permeates pretty fast. With technique 1, you won't get this detail. You'll never know if the methanol is permeating or not. You may, however, make the assumption that because it doesn't permeate when it's pure methanol, it also won't permeate when it's in a mixture. This is why technique 2 is critical. A key thing to restate here is that mixture permeation isn't detailed in any of the industry standards. Here at Ansell, however, we like to develop our knowledge in permeation science, enabling us to go above and beyond the standards. As well as being able to test mixtures, we currently have a collaboration going with the University of Hull. This is through what is known as a KTP, a Knowledge Transfer Partnership. In this 3-year project, we're really trying to develop our mixture testing capabilities and really understand how mixture permeation works. This will enable us to perform informed estimations and develop models for the millions of mixtures that no one will be able to ever test.